basically, I'm going to present about our survey. We try to understand what the simulation practitioners really need from cloud computing, or from the cloud simulations. So I think I copy Barry Nelson's approach when he presented a seminar at Lancaster. So in case there's a fire, at least you can get the idea of what I'm going to present. So put some of the highlights of my presentation first. So basically what you will see is that our objective is to study the needs and perception from practitioners on cloud-based simulations. So that is the objective of our pilot study here. So the next one is that to do this, we survey 86 practitioners, academic. When I mention practitioners, I mean that includes academic and industry, both of them. And the findings, basically, if I can just take two main findings, is that they have good exposure to cloud applications and mobile gadgets. And the second one is they kind of come up with the what they expect from cloud-based simulations. Okay? So that is will be those are the highlights of my talk today. Okay. So this is the outline. Basically, I will talk about what cloud-based simulation is, followed by what the survey design, findings, and conclusions. Pretty straightforward. So, just to make sure we are on the same, on a common ground, there are too many definitions of cloud computing. So I just pick one from. There seems to be de facto definition. So, but just pick one. It's called from NIST. It's a model for enabling ubiquitous. So I highlighted a few keywords there because it's really worthy definitions. So ubiquitous, on-demand, shared pool of resources, and configurable. So we can configure that, and we can also provision them very rapidly with minimal management effort. So that is the idea of cloud computing. Okay. So basically, if we can summarize what cloud computing is, it has a few characteristics. The first one is that it should be on-demand self-service. So this is on-demand. Resources available whenever we need it, and it's self-service. We don't. So the involvement of the vendor will be as minimal as possible. And broad network access, I think, using multiple platforms like mobile devices, laptop, desktop, and so on and so forth. So that's why in the questionnaire we are also interested about mobile gadgets. So it's try to understand how practitioners may use the cloud-based simulations. Resource pooling, so the resources are pooled somewhere. And rapid elasticity, basically, okay, if the demand is up, we need more resources. So that can be deployed automatically in the background. So that's the idea. And finally, as a measure service, because at the end of the day, it will not be sustainable if there is no, if someone has to pay for it. So what kind of measure services that we, can be introduced in cloud computing? So I think yesterday I talked to Shinran about the possibility of pay-as-you-use model of one of your brewery model. I think if you haven't seen the brewery model, I think you can probably go to the Secure Solutions booth, and it's one of the idea about if you're running a small business like brewery, and then you want to use simulations, probably you can't afford buying massive expensive simulation software. So that's the idea. Okay, so why don't we use the cloud-based simulations? Run it once, and then you pay for it. So that's the idea. Okay. So the next one is the service models. So how can we deploy such cloud-based applications? Well, we can do it as a software as a service. So you run the software over the using a web browser or something similar, and then they basically run the software using pay-as-you-go. Another alternative is platform as a service. Basically, okay, what if I want to control the application more? So I can write the applications myself, modify it, and then run it. So this is a bit of a step from the software as a service, because this one is just given, I just run it. the software has been developed for me and just run it. This one, I want to develop it myself, or at least I need to reconfigure it myself. The next one goes even further, so it's infrastructure as a service, similar to past, but now I want to control the environment as well, like operating system, database, and so on and so forth. Okay. Now, if I want to relate this from cloud computing into cloud-based simulations, what would we expect from cloud-based simulations? One that I could foresee, and I think it's demonstrated very well for using the Blurry simulations, is that simulation as a service. So someone has developed a model for the user, and then the user can run it, maybe for a fee, or for free at the moment. All right. Some people, they may want to be a bit more than that, so we call it, say, modeling as a service. So this will allow people to build the simulation model or configure the simulation model over the cloud infrastructure. So it's not just running it, but they want to do something about the model, modify it, or even build it from scratch, probably. So let's call this modeling as a service. And the next one, probably we can simulation platform as a service, just to adopt the name platform as a service from the previous slides. In this case, we expect the consumer can reconfigure the tool itself. So it's not only building the simulation model, but the tool to build the simulation model can be reconfigured. So for example, I like, say, Barry Nelson's optimization algorithm. I want to use that algorithm and then plug it into my simulation tool. Or if I like, I don't know, Pierre Lecuyer random number generator, just put in one and then plug it into my model. So that's the idea. So if I can reconfigure my simulation development tool, then I will get what I call a simulation platform as a service. Again, it requires certain interoperability, which you've been working on, right? So all the standards. So we need the components to be interoperable. The next one is probably go a bit further for simulation infrastructure as a service. So in this case, we want to have a more control. So say, for example, I want to set that my model should read a data from certain data server that I can trust, because I don't want to put my data on a server in a country that, say, I don't know, has a less strict requirements on privacy, for example. So that is a big issue for some people, if not most. So if I can control that, and I can control the execution platform as well, or I think we just discussed about the middleware, about the distributed simulation. If we run multiple simulations at the same time, can I choose the middleware instead of using, I don't know, Particle or use something else? Yeah. So basically, I want to have a bit more control about what is happening, how I want to run my model. So that is what I call simulation infrastructure as a service. Okay. So the next one is, okay. So now the attempt to use web technology in the past actually has been done quite significantly, what we call web-based simulations. So we really want to learn from what happened to web-based simulation, because you probably can disagree with me, but I find that web-based simulation was not really that successful in gaining commercial adoptions. So try to understand what happened. So one of the reasons that I quite like, it was suggested. I think Paul suggested this one, is that the web-based simulations, they thought that my web-based simulation was not successful because it was simply implement the desktop versions into a web-based versions, and so the web-based simulation did not really exploit the new features that web application could offer. Yeah. So I thought that could be the same for cloud-based simulations. So we can't really, probably we must not simply implement the existing desktop simulations into cloud-based simulations. We need to exploit the specific features of cloud computing that probably we can do something differently now. that probably was not possible using desktop computing. Desktop simulations. So try to take full advantage of cloud features. So we need to think probably outside the desktop simulation box. Okay. So and the next thing that I think probably one of the reasons that cloud-based simulation can be a failure, it should not be seen as simply a technological tool. We need to see it as a socio-technological tool, socio-technical tool, because we also need to take into account that there are users there. We need to know what they really need from cloud-based simulations. So that's the motivation of our pilot study here. So we did a survey, and then we got responses, quite a significant number of responses, and then we did just a bit of information. We collected the data early last year. We distributed in a number of LinkedIn groups, mailing lists, and I think we approached Lineage and Simulate as well to distribute the survey, the questionnaire to their customers. Okay, so basically, who the respondents were. I hope you can see. So most of them, roughly about 33 respondents out of 50 something, they come from university and research institutes, followed by consulting, healthcare, manufacturing. So I think it's a pretty good distributions of sectors in the industry. So they are quite well represented in the survey. Most of them, if not all of them, most actually, except two of them, most likely they are academic. They usually work in groups. Okay. So, and I think the most common size is about between 3 to 6 people in a group. So maybe if you can, I don't know how many people usually in your group, for example.
In the group doing a model, or in the team?
In the whole project team. Yeah.
And in a project team, normally it's one person in that project team. Okay. But obviously there's lots of project teams going on in parallel.
Right.
But they don't tend to work in a group, so surprised by that.
Yeah. Right. So the next one is the frequency of model development. So we can tell that most of our respondents, they build simulation model pretty regularly, at least monthly or at least 6 months. Some of them do it even weekly. So basically the point is that they really know, they've been using simulations almost very regularly.
Sorry, Stephan, can
Yeah.
I just ask you a question?
Yeah.
Are you really saying that people in a team of more than 50 building a simulation model?
I haven't really, I think I can roughly guess. This is from one of the big organizations.
I think it might be down to misinterpreting the question.
Yeah, could be. Yeah.
Is it the size of the organisation or the size of the people
Yeah.
in a given project?
That's right. Yeah. It's probably the size of the department he's mentioned.
Yeah.
Or it might be significant, you never know.
That's quite a lot of it, isn't it?
Well, it probably isn't much of a model, actually.
Well, yeah.
Right. And then one of the things that we are interested is because one of the things that cloud-based simulation can be quite useful is for communications. So we are quite interested in how do they approach, how do they communicate with members within their team and with clients. So it's not quite surprising, honestly. So within the team, most of the time face-to-face, followed by email. It's pretty straightforward. And the difference between communication within the team and the media, with the client, is that email, because clients usually is outside the organizations, so email is more frequent than face-to-face. But one thing that we notice is that people were using teleconference, online messaging, and video conferencing. Although probably not many, but it's quite significant because these are in percentage. So it seems that people have been working quite remotely. So it means it can mean that some of the team members may need to travel somewhere and then they still need to communicate, or maybe they are based in different locations. So they work together as a team. We can also see that from the communication with client as well. Okay, so that is the communications. And then we are quite interested in the tools and gadget usage because we want to know whether our respondents are familiar with this one. So that is a kind of positive indicator whether they can be adopters of cloud-based simulations. So whether it will be easy for them to adopt cloud-based applications or cloud-based simulation in this case. So we basically ask them a number of tools or gadgets, and then we ask them whether they have used it for a simulation project, or they use it for at work, but not for simulation project. They use it socially, or they never use it. So we can see that most people have already used remote desktop and cloud storage for a simulation project. So that also gives an indications that many people, they probably travel quite a lot, maybe visiting clients, or maybe they work in separate locations. And then because remote desktop, if you don't know what remote desktop is, it means that I can actually show what is on my desktop to other client. Oh, sorry, I can control the desktop from the other client, from the other party, and then show them how to do things from my computer. So then that can be quite useful if you work with someone on a different geographic locations. And then cloud storage, I think everybody probably have used it. Dropbox, for example. Right? So it's quite handy. So for example, if I fail to copy my file here, or I lose my USB stick, I still have one in Dropbox, so I can always download it, provided we have internet connection here. Alright, so, and the next thing is that he also used smartphone, for example, but again, this one, I think for the next version, I will need to ask more specifically, smartphone not as a phone, but as a mobile applications. So I think I can, so I completely missed that. Because when I check this one, some people might interpret it as making a phone call, but we are not interested in that in this case. We are more interested in mobile applications. And then LinkedIn, they use collaborative writing as well, and this one is using tablets, writing wikis. Because I know that in some companies, they quite often, especially when they need to write manual or user guide and involves a number of teams, they do wiki as a start. So they write a wiki for the team. So it seems that some of them have already done it using this. So it's quite an interesting finding. So we didn't know about that before. I know this happens quite often in the simulation, in the software development team, because they do this quite often. But apparently it is done among the simulation team as well. Okay, this is the last part of the survey. So we asked the users, okay, suppose you have a stable and fast internet connections. So we need them to assume this. And what would you expect? How do you rate the following features? So I think it's not surprising that most of them will rate fast response time to be what they really as their first priority. So you can see here, essential. The blue one is essential. The red one is good to have. So we are looking at the high blue and high red here. So the next one is basically others to comment on the model, others to run the model. So we can see, because they are interested in other people to comment or run the model. So we can see the requirement there for another communication, another feedback from either team member or clients. And then the ability to share model, store or retrieve models, I think come up quite significantly as well. The one thing that is not very significant is the ability to edit models or others to edit model. So I think we need to get more data from this one by interviewing people. But my guess is because not all of the respondents are probably model developer, because we asked roles as well. I think you can see it from paper. some of them have a different role, like project manager and so on and so forth, simulation analyst. So they don't really edit the model, and they don't probably. So their mindset's probably more on the. I prefer to edit the model using desktop computer, and then store it on a cloud computing computer somewhere, and then run the model or let other comment on the model on using cloud infrastructure, but don't touch it. So basically that is the key findings, and that is the summary. So basically from this survey, I think we kind of have a better understanding of the perspective from the simulation practitioners about their modeling work, their exposure to cloud-enabled applications, mobile gadget, and the application of the functionalities that might be offered by cloud-based simulation tools. And thank you for your time.
Do we have any questions for Stephen? There must be some questions.
Yeah, Charlie.
I was interested in, who the people actually were and what they were currently doing with it. Were there people who were, is there a particular kind of person or software that were using it a lot more than others?
I cannot really tell directly, but because the way I distributed the questionnaire, most of them I suspect are discrete event simulation modelers, because the LinkedIn group that I used was, I know from the member names that most of them are discrete event simulation modelers.
Just sort of two things to say before I start. The idea of using a large resource pool to run applications running on people's computers isn't a new idea. If you go back to the 60s, we had a mainframe with remote terminals that shared resources on the mainframe. And what we've seen over the years is sort of an expansion in the scope of that core computing functionality. So in some ways, when you sort of say cloud, what you're really saying is a convergence of technologies to make a large amount of computing resources available in a, I'd say, relatively simple ways. We're going to say it's not such a case. But it's also then it's sort of how the term cloud is being used. So when I first came across cloud computing, because I'm a computer scientist, so I play in that area quite a lot, obviously. And I'm also a complete geek. I love my gadgets. Cloud was all originally about communication and nothing to do about computing and data and storage. It was about being able to walk from one end of London to the other and have uninterrupted network access. That's what it was originally. And then slowly it was, well, let's maybe make data stores available. And really, for me, the transition to cloud is basically when the big IT companies grabbed it as a marketing term. So if they hadn't, we might be using the term as, galaxy computing or sky computing. So it's kind of a sort of synthesis of a good idea with a bit of marketing thrown in. So that's my sort of 10 pence of context. But it's definitely a term that's here. So what I want to talk to you about this morning is a new, I say it's new, it's been going since July, and it was originally conceived about a year and a half ago. This European grant that I'm running on called Cloud SME. And Cloud SME is all about trying to get a change in the way that we use and supply simulation to end users and practitioners, etc., by using cloud. And I'm going to give you an overview. And Russell made a comment about, I don't know how complex it is. Well, around about slide 5, I'll show you. So the co-authors, and this isn't the full set of co-authors, but myself, Thomas Kiss is the project leader. He's at the Centre for Parallel Computing at the University of Westminster. And that's great for me because I used to work there 20 years ago, so it's quite nice to come back there and work with these guys again. Peter Katchuk is a visiting professor there, but he's the lead at this institute called MTA Staki in Budapest in Hungary. And really, they've been driving research infrastructures in the European Grid Initiative for a very long time, so it's a very mature group. Then we have Gabor, your guess is as good as mine, I call him Gabor. He's a professor, he's the lead of the Centre for Parallel Computing. He took over from Steve Winter 2 or 3 years ago. And then Nicola Fantini, who's the CEO of an organisation called Cloud Group, who supplies some middleware that we use, I'll describe shortly. So overview, all very simple. If there's a fire, run. These are your highlights. I'm going to give you some cloud computing context that Stephan's already given you, but I'm just going to think that people got short-term memory, so I'm going to run through that again, ask questions later. I'll give you an overview of the Cloud SME project, and being an FP7 European project, of course, there's a huge number of partners and all that, but I won't go on too much about that. I'll dwell on the Cloud SME simulation platform, which for me is the most interesting part of the talk. And then I want to say something at the end about simulating cloud computing, because there's a definite point I want to make there. What I haven't got in the talk is the brewery template, so if I've got time at the end, I'll mention that. And is the demo up and running on the Sega stand?
It is, yeah.
Yeah, so Sega's involved in this as well. Maybe say something about that then. Okay, so all presentations about cloud computing usually start with a misdefinition. I'll decide not to. I'll give you the motivations instead. So in my area, you usually come across cloud from starting to say, well, how do you make things go faster? Well, the usual response, certainly in my university, is, well, I need money to do that because I want my kit. I want my cluster. You go around Brunel, it's the same in probably Southampton and all sorts of other universities. You have academics who have their pet clusters, usually in a cupboard in their office, overheating. They need tending like sort of irascible ants, and they don't usually work together, but it's mine. I can do anything I want and it's there on demand. So I buy hardware, and hardware makes me happy because I like kit. I then hire more people to manage and support the growing clusters, okay, or networks of PCs or whatever. So I'm being an academic, I get research fellows, and I worry intensely that in 2.5 years' time I have to find another research fellow or continue the grant. So it costs more money to do this. And then I build cluster after cluster to power mission critical applications. So you end up with sort of large data centres which are extremely costly. And if you're Ford or whoever, you can afford it. But if you're an SME, you can't really do that. So the problem is low average utilisation rate. So I've got a big problem, but that problem only exists for a short period of time. And if I've got the clusters, it exists for an even shorter period of time because I can run things faster. So I now have a very large paperweight in my office, costing a lot of money to run, not really doing very much, and is already obsolete. Wasted capacity. There's loads of things. Loads of wasted capacity in my cluster because it's not running. One of my little bugbears about UK universities is there's loads of PCs in all these unis that, as a taxpayer, I've paid for. I'd love to be able to use that spare computing capacity for British industry, instead of, say, Facebook or any number of applications that our computer science students use. Out-of-date hardware. I mean, I can't remember who says this, but there is an adage that as soon as you buy a computer, it's obsolete. Being a geek, as soon as I buy something, I want another one. I want it better. I want to have more cores. I want to have GPUs. I want more RAM. And it's in my office, and I feel very happy when I see it gathering dust. Expenses to manage and maintain, particularly if we've got sort of more esoteric operating systems. You usually have people these days in universities, certainly in organisations who are good at running Windows servers. You need to revert back to Linux, Unix. It's a bit of a shift, etc. And again, too costly for SMEs. So, use cloud computing instead, and for those of you who've got good memories, lasting more than half an hour, this will look familiar. This is my version of the NIST definition. So, on-demand self-service. So, I need speed, I get it. How you do that is a little bit more complicated. Broad network access using more platforms. I always found that interesting coming into a definition about cloud computing, but that's just recognising that maybe one day we want to launch cloud computing applications from our telly. I want to optimise what I want to watch this week, go and work it out for me quickly, silly example, but it's not unrealistic because, I mean, I remember somebody from Daresbury, which is a big physics institute in the UK, coming to visit Brunel 15 years ago, and he said the internet is dead. One of the times around about 2000 where there was all of these talks, and he said the internet is dead. Well, I don't mean that. The way we access the internet is dead, and one day we'll all access it through our televisions. And I said, oh, what do you mean? Of course, now you buy a modern smart television, the least of the things you can do is watch TV. Whilst you're faffing them with the applications trying to find BBC One. Then you've got rapid elasticity. Now what that means is I want 1,000 CPUs and I want it now and I want it for 10 minutes. And when I've done that I want to get rid of it. I don't want to pay for it anymore. And I get that instantly. Now that's the theory. In practice it's a little bit more complicated than that. But I get what I want. I can scale up and scale down. If I'm running a business like Amazon, I want to have more data centers, more data servers available to service my customers. If I'm nationwide, I want to be able to access more servers, particularly in the week of the ISAs. Everybody suddenly remembers they haven't got an ISA. Clearly, Nationwide doesn't have this system from personal experience this week, but it's sort of crashing. Not a good way of running a business, but there you go. Different business models. I buy a computer. It rots away in my office. I'd like to hire a computer. I want to use software. Usually you get software on a yearly license. I want to just pay for use. Now that is very simple to put, but there's a lot of debate about what that actually means. And certainly in the Cloud SME Consortium, in certain ways, we don't know what the business models are yet. And it's quite fascinating listening to the different ideas that are coming through. And then it's an access to high-performance computing, so general or dedicated hardware to speed up applications. So cloud technologies, again, Stephan's already said this, but I've got a pretty picture to go with it. It's basically you access it through a gateway. Then you have software as a service, so software deployed as a service in a cloud. And what that means is you have to do certain things to a software application so it runs on a server. And a lot of software I come across on a daily basis, that clearly can't work. It needs some work. I think when things are being deployed on a server, say for example NetSim and iThing, you've still got to do more work to it to make it interoperate with other software. You run platform as a service. Now that's all the gubbins required to actually host a service and provide something as a saleable service to a customer. Infrastructure as a service is the resources. So if you are a cloud provider, you'll probably run infrastructure as a service, and you've got all your clusters and servers behind you, running some software to allow people to host their services on that, and you charge for that use. And then you can have a gateway through to high-performance computing. So, and there's also, and I mentioned this in the paper, and Stephan mentioned this as well, there's some people sort of coming together trying to say modelling and simulation as a service, and I think that's got some merit, because there are some things about simulation which are quite different to normal software applications. You've got different models, you've got different types of cloud, you've got private cloud, community cloud, public cloud, and hybrid cloud. Don't need to really go into that, just to recognise that companies offering clouds are different to universities offering clouds. All those are slightly different in the way you access things. Different resources. Well, I can offer a cloud which consists of computers having a single CPU, or 2 CPUs, or 4 or 8, or sometimes 16. And those have particular footprints which are very useful for different applications. I can have GPU specialist hardware, and I think Russell's going to say something about that in the next talk. So I can hire my GPUs for vector computation, for example, and then get rid of them when I need. Dedicated high-performance computers running MPI and dedicated parallel languages, and various types of different storage. And then just to make things even more user-friendly, we have different middleware running clouds, which are incompatible. So I could have a cloud running OpenStack, running some applications, but I can't easily port those to OpenNebula clouds. And there's loads of different ones. Amazon run a different one as well. So, how can you create simulation applications as a service that are easy to use, can run on different clouds using different operating systems, can use high-performance computing, and can be easily reconfigured and interoperable? It's not easy. So this is why we came with our consortium, Cloud Computing Simulation, Cloud SME. We're aiming to make that easy for simulation vendors and users. There are lots of people involved, lots of companies, and we're going to expand and bring in more at some point as a sort of user forum. But I'll talk about each of these in terms briefly. This is a really good case for cloud computational fluid dynamics. So lots of Monte Carlo simulation looking at fluid flow. So the companies involved in that, Ascom is a Swiss company. They produce software called Transat. The Transat's used in oil refining, oil drilling. It's used in wind turbines. It's all about looking at flows through things. Each iteration of a Monte Carlo simulation takes ages for them. So it's a really good fit for cloud. They need speed up. Their end user is Eurobios, so they're a consultancy, uses Transat to consult with the oil industry to solve problems. Process simulation. This is more challenging because simulations, discrete event simulations, run quickly. So why would you want to use cloud? And this is Mark and Shane, in this use case, managed to convince them about a year ago to come on board with this this merry band. And we're still asking the question. So we're creating the technology, but it's kind of as a sort of, well, let's see what will happen when we do it. Because something which seems to come out of Stephan's survey is, well, if you can't do it, well, you won't do it. So the question is, if we had a different deployment of Simulate, what could we do with that? And one thing which has come out, which is very exciting, is the idea of web-based or cloud-based templates. So we're trying out the idea with a UK brewer. And the idea is that, well, are all brewers the same? Or if they're different, can we capture the core business so they can use, what would you say, simulation as a calculator?
Calculating.
You know, and so can we provide, and in some ways that's what the promise of web-based simulation was 15 years ago, but can we deliver that with a professional consortium behind them? Then we have the 3D insole design. I should be doing this. There's another diagram. This is all about shoes. Now I think this is probably going to have the highest impact in the Cloud SME project initially, because there's a very simple use case. There's a company who sells a 3D modelling tool. So you go into a foot doctor, put your foot in the cradle, you get a scan of your foot. That's then sent off and modelled. It comes back, it's checked. Meanwhile, you've gone off and done other things. So what we're trying to do with cloud is make that instant. So you get a scan, you get the 3D model back immediately. You check to make sure that's fine. And then you send off and you get an insole design. Now, there's a huge number of people with foot problems. So the cloud, the added value for cloud for them is that they're going to be able to spread that out across Spain. And what they want to do is then reach into the Brazilian market. So I think that will have a big impact across the international boundaries. And then the last one, for now, aircraft logistics. This diagram doesn't really show it. The idea with that is there's a company that can gather real-time maintenance data for aircraft. And the idea is you use cloud to do high-performance mining of the data to see where to put your spare parts. So obviously spare parts cost money. So the architecture that we have, the Cloud SME simulation platform, starts off quite nicely. So we have an environment called WSP grade, where basically you describe your workflow. Now most simulation applications tend to be upload what you want to do, have it processed, and then give back the results. There tends just to be 3 boxes. But it's very simple, it's drag and drop, you put your boxes onto a pallet, you join them together by arrows, and the arrows indicate file transfer. You then open up the boxes and you specify what you want to do in the boxes. So the boxes initially are dummies. So you've got to put the tasks in there. So you describe what application is going to be used, and how it's going to run, and then where it's going to run. So you can't read this, but basically this is saying use Cloud Broker and use the Hungarian cloud. That workflow is uploaded to a server called the GUse server, which when called, calls the instance of your simulation software and runs it on the cloud that you specified. Now, that's the promise. As we know, the truth is a little bit more buggy than that. But as ever with these sort of software projects, it's sorting out quite a huge middleware stack. So the architecture behind that is we've got the P-grade user interface, we've got workflow storage, so that you can deploy on your GU server. Anybody else can have a WSP grade web application to access the workflow. You call it, run it, you get your results back. Nice and easy, but quite a lot of stuff behind it. Now this has actually been developed for generic DCIs, distributed computing infrastructures, so you can actually pick up, and don't worry about what's down here, but there's a huge range of distributed computing infrastructures in addition to cloud that this system uses, because this has actually been set up for European research, and it's been redeployed now into simulation, or modeling and simulation. Now, if we select cloud, we then go to Cloud Broker, and just following up Russell's, how complicated is it? Well, I'm not going to go through any of these boxes at all, but just to say that there's a lot of things that you need to do to manage the cloud. But the beauty of it is, you just see it at this level. So when you deploy things, I want to now deploy this on Amazon, you go back to this level, pick Amazon, and run. That's what the overall architecture looks, which I don't really like that diagram at all, but the idea is that you've got the end users, which in this case are Eurobias, Seika, Productiva, and Tomorrow. They've got their plug-in front ends of their software, maybe running in a web browser or connected directly into the application. Ignore the rest, up to this level where the software is deployed within Cloud Broker, and then there's specific deployments on a variety of clouds at the bottom. So there's a lot of work that has to be done first, but once it's there, the end user can pick a menu option and run. They've got a different version of this, where they call it the one-click version, the one-click architecture, I think it's called. That's it. Where you can say, right, set me up an infrastructure for 2 days and let me play around with it. And that's been delivered for an application called Autodoc, which is a molecular modelling software, and that works really nice and easily. So, winding up. Cloud computing is highly complex. Cloud SME simulation project is trying to simplify that. End users will benefit from simulation applications that make use of cost-effective elastic cloud computing, but it isn't simple. And this is the byline I came up with, Mark. It's easy. So, excitingly, this is Simulate. This is the future. Starting here. It says Simulate up there, so you know. This is the preferences page in Simulate. And Mark did this unprompted. And my first response is, you sent me the use case document, where on earth is the cloud? And Mark added this circle down at the bottom. This is the vision for Simulate, that the end user doesn't see anything at all, really, apart from this box down here, which says, permit cloud to accelerate results. Now, I've got other ideas about that, which is kind of automating confidence intervals. So if you want to go from 95%, well, why not go to 99? You've got unlimited resources in the background. So we're experimenting with all sorts of different ideas and how to deploy that to the user. One of the things that we sort of ran in terms of cost effectiveness, and these are very raw figures, because we can't run this at the moment, so it's not quite there, but it's very soon. We ran Autodoc models, which take about 39 seconds a run. And we said, okay, let's run 1,000 of them using 100 CPUs on the Stacky Cloud in Hungary. We got a 48 times speed up, which isn't great, but it's okay. It's reduced the computation time from hours down to minutes at 2,500th of the cost of getting 100 processors. So 1,000 jobs running at 39 seconds, 48 times speed up, 2,500 times cheaper than buying the hardware itself. Okay, so that's a good line to end on, I think. So, thank you. Any questions?
So, some exciting questions for Simon then. He said it's easy. Yes, sir.
I would like to ask about licensing and, for example, Simulate has a license to buy it. If you have to provide it as a service, does it imply more cost?
Well, this is, I could say within Cloud SME we have a work package dedicated to sorting out the business model. but that would be a bit of a cop-out. We don't know. We don't know. There's a lot of sort of field of dreams to this sort of thing, that we're building these as a sort of a way to sort of maybe transform the field, but there's a lot of unanswered questions. So we could say, well, yes, we could have pay per use. Yes, we could give it away free. Yes, we could do this. Yes, we could do that. But it's largely untested. And one of the reasons why is that we don't know what users are going to react to this software. So I can say we could have a version of Transact that is pay per use computational fluid dynamics. But until you can start playing around with that and see what the value is to your own company, it's difficult to see how you can justify it. Because at one end I could say, now this is a university researcher, it would be great to have a pay-per-use high-performance computing version of Simulate, but I would need to bid for that in a research proposal. And research proposals are more geared up to buying software licenses. If you're in a company, companies are geared up for annual maintenance fees and costs. You know, I'm going to go to my CEO to say I need 100 quid to run super fast on this application. I'll probably get a better response if I said £10,000 than 100 quid. But, well, we're not geared up that way because our accounting and year-end numbers don't follow that process. So there's lots of different factors in play. But if you look at cloud computing across, you know, outside of the project, there's no single business model.
Can I follow up from Simulate's point of view? I think it's genuinely the case that we really haven't a clue what to do about licensing. So part of the reason for being part of this project is to do a whole lot of experimenting and see what works. And I personally think that if we could just make cloud use of simulation completely free, then it would drive demand for model building, which will drive up our revenue anyway via desktop versions. So ideally we'd make it free, but then you've got problems that, you know, the Amazon cloud is not free. So you've got to have some way of working out how you can charge for that.
Yeah.
But it's really open question.
And let's not forget that Simulate already has a cloud implementation. Can you get this use Simulator, isn't it?
Yeah, and now we've made that completely free.
Yeah, so you can upload your models to the cloud. In this case, it's Amazon.
It is, it uses Amazon.
Yeah, but that's irrelevant. It's a cloud, which means you can deploy your models online, and Simulate provides that as free. You know, I mean, it's a question of, you know, using that example. You know, why would you want to run a 39-second model 1,000 times? Well, I couldn't sleep last night because I was trying to come up with the answer, and it's sort of, let's say you do 10 reps for a 95% confidence interval. Well, why not do 20 for 99%? That brings it down, and sort of, well, it's really sort of doing two experimental parameters. So one has a range of 5 values, one has a range of 10. You're doing 20 reps for each of those. That's 1,000 runs. I don't want to wait half a day for that. I want to have that in the next 10 minutes. So if you use 100 CPUs, you get that result back. That's quite a compelling argument. And so some of the discussions I've had with Mark, well, rather Mark's idea, is that if you're doing 95, well, I'm transparently kind of not force the user to do 99, but just sort of have that on offer. Did you realise that these results are there? And sort of try and get community used to, well, Simulate does this as a matter of course. This is really cool. Why didn't Witness, why isn't any logic, why didn't Flexible do that as well? So you get the demand out there, and then that they innovate, and that comes back to Simulate and all round and round. Yeah.
I mean, one potential area is in real-time decision-making using simulation, where you might want to little bites, but you then want the answer really fast. So perhaps a cloud-based solution might be very attractive.
Yeah. I mean, for our current 4 use cases, computational fluid dynamics, it's obvious why they need cloud, because those are massive computing problems. For the 3D foot modelling, I mean, it's, in some ways they need web hosting, but cloud just makes it easier for them to do it and to operate with the other tools, and that's good. Aircraft logistics, big data mining problem, great. And so the one use case we have where there's a question mark is discrete event simulation, and that's quite fun because we don't know where we're going with that.
Simon made a rather sort of witty sort of put down of some of us with geeky.
I'm quite scared now, Russell. You're extending your.
I've actually, yes, the screen doesn't come up quite right, but anyway, that's perfectly okay. Can I just double check the screen, because it looks a bit odd. Well, I'm not quite sure why it's not showing the full thing. Okay, well, this is really about hardware, and it's about massively parallel processors. Sorry, not quite right. Here's a talk outline. It's about personal massively parallel programming, and about general purpose graphics programming units in particular. And I'm going to talk about a particular hardware and programming platform called CUDA. Now, CUDA's been around for a while, so one thing I'm a little bit nervous about in this talk is that this is a topic that's new to me, and I've only had very little experience of it. I know that GPUs have been around for a while, so it may be I'm perhaps the least expert person in the room to talk about this. So just as a sort of check, how many people have actually written a CUDA kernel program and executed it? One person. Okay, so most of the audience then will not be too familiar with what I'm going to be actually sort of talking about. So I'm actually going to talk about some of the hardware characteristics of these general purpose graphics programming units, the typical program structure, and I'll give some examples from simulation, a discrete event simulation example, and some simulation input-output analysis. Here's the actual type of card that does all this, and this is actually the card that I've actually got. And the important thing about it is that it actually fits into an ordinary workstation. So as Simon was saying, it's something which is rather geeky in that here I'm actually at home. I didn't actually bring it with me, but I have actually a photo of the thing. It's actually sort of lurking there, it's switched on the screen, and I'm hoping yes, I look sort of slightly insouciant there, but that's a super computer. And the nice thing about it is actually sort of sitting there at my beck and call without, sort of trouble. It has been applied in quite a number of areas: particle physics, financial modelling has been used quite a lot, and also quite a lot of statistical analysis. But it seems as if that we in simulation haven't sort of made so much use of it. And the point of this talk is really to assess the usefulness of this hardware in simulation studies. And the initial conclusion that I would draw is that it's potentially quite valuable, particularly in more statistical type applications like input-output analysis, especially when there are sort of large data samples involved. CUDA, this Computer Unified Device Architecture, is probably the leading massively parallel computer platform, a programming language, and hardware involved. And the attraction of CUDA is that the language is actually effectively C. Well, I'll show you some code a bit later on, but it's really a very simple extension of C. There are other approaches that I should mention. Two here, thrust and array fire. These other approaches are trying to sort of avoid the user having to get too involved with the parallelization side, and thrust and array fire are essentially suites of subroutines providing most commonly occurring basic calculations. At an even sort of slight higher level are OpenMP and OpenACC, which basically allow you to insert directives into your own non-parallel C code, which give an indication to an appropriate compiler which segments you might try and actually parallelize. The card that I've actually got is called Tesla, and it was really the first generation of graphics processing units designed for general purpose computing. There have previously to that been various adaptations of what were essentially graphics cards, still with a lot of emphasis on the graphics side, where there was already a lot of basic parallelization required for rendering pictures fast. The card, however, though it is suitable for general purpose programming, it is still strongly influenced by their graphics origin, and this really determines and limits to quite a great extent what you can do with them. So these are really the sort of key points here. The GPGPU is basically a set of identical streaming multiprocessors, each of which is made up of a number of individual streaming processors, SPs, usually called cores. The core is really the equivalent of a CPU, not quite as fast, but getting there. So the number of cores gives you a broad indication of how powerful the card actually is. When it's been executed, each core runs its own piece of code, the thread, and the threads are arranged in blocks, and these are arranged in a grid. The way that you usually operate a GPU is using an accompanying CPU, the host, and the GPU is really called the device. The parallel bit of code, the thread code, is held in a subroutine called a kernel, and that's the only bit of parallelization, at least you need to worry about initially. And the sort of typical form of a one kernel application is set up like this. You select the actual grid and block size to be used in the device, which fixes the arrangement of threads that you're going to use. Allocate host memory for input, output, and similarly on device memory as well. I'll say more about that in a moment. Then all you need to do is then just put the input data into the host input array, copy it over to the device input array, then launch your kernel and pass over control to that, which then executes the threads in the device. So this bit in red here is really what is being sort of done in parallel, and the results are then put back into the host output array, which return control back to the host for you to do what you want with the results. So that's the basics of a form. One key issue is the copying of data from the host memory to the device memory, which are physically separate. And this is one of the time-critical aspects of the work. There are actually 6 levels of memory on the graphics card. The most important is the shared memory and the global memory. The shared memory is, there's shared memory for each of the streaming multiprocessors. It's shared by all the threads that run on that streaming multiprocessor. It's on chip, very fast access, typically just a few cycles to access that memory. But the memory size is rather small, so this is a critical limiting factor. You've only got 16 kilobytes on each of the streaming multiprocessors. The host can't get at this memory at all. The global memory is basically just dynamic RAM, and is shared by all the threads of an application. The contents are held there for the entire application. It's off-chip, so access is very slow. It usually takes hundreds of clock cycles per access. So this is clearly a very limiting factor. But it's a large size. I mean, it's got at least hundreds of megabytes of memory there. The other key thing to note is that The threads, these are the actual codes run by the individual cores, do not run independently. Blocks of thread are assigned to specific streaming multiprocessors, and usually you send more than one block to each streaming multiprocessor. The threads in a block are then split up into groups of 32 called a warp, and this is what is presented by the streaming multiprocessor to its cores. And this is the key point in the way it operates. The threads in a warp, once it's presented for execution, the instructions have to be carried out in what's called lockstep. All the cores have to carry out the same instruction at the same time. A thread can skip an instruction if you can't perform that one, but all is not lost because there's actually quite a lot of control exercised by the streaming multiprocessor, and the warps are actually queued because each streaming multiprocessor has quite a number of warps to work with, and these are queued, and there's the online operating system, sorry, the operating system of the streaming multiprocessor, each of which has its own operating system, will actually handle the queuing and pick out appropriate warps to run as and when it can. So there's quite a lot of intelligence involved in that, which one doesn't see. The card that I've got is the C2075. In fact, I've been sort of on the lookout for a card, and they're really sort of quite expensive. Even now, a brand new one is still pretty expensive. It's about sort of £2,500 sort of pounds, which for an individual, certainly a retired person, is a bit steep. But I kept an eye out on eBay, and about 3 months ago, this card, second-hand one, came up for £600. So I took a risk and bought this thing and took it around to the local computer shop. I should say that for those who don't know, I live in one of the least populated parts of England, Ludlow in Shropshire, and it's amazing that this computer shop actually had someone sufficiently interested in this to build me the workstation to put the card in, and it actually worked. So that's why I've got this supercomputer. It's got 14 streaming multiprocessors, each with 32 cores, and that makes 448 cores in total. So that's the sort of power that's available. If you choose a block size, therefore, which is a multiple of 32, this divides up nicely into a whole number of warps, and a block then can be handled by each of these multiprocessors very neatly. The core, each core runs at a frequency of just a bit over a gigahertz. The actual CPU host chip is an Intel one, which runs at 3 gigahertz. So that gives you an idea. So these cores are not as powerful as the CPU, but it's still reasonable. The attraction of this is that it was the first of a generation that would deliver proper double precision floating point performance, and with all 448 cores blasting away, you get up to 500 gigaflops, and if it's single precision, you're in teraflop territory. You've got million floating operations per second. The GPU has 6 gigabytes of DRAM, so it's pretty large. Though this card has only been around for less than 3 years, it's already considered, and this is something which Simon's commented on, that it's already not good enough, in that it's called legacy hardware by NVIDIA, the manufacturer. One thing about all these is that they do get rather hot, as again, something that Simon sort of mentioned. This has its own little sort of cooling fan on the actual board. Later cards, like the K40, which is one would like to aspire to, has got 2,880 cores. In fact, the one which is almost become sort of affordable is the K20, which is 2,496 cores, and that sort of Still over £1,000, but it's sort of getting there. So that's the next one to last after for a private user. Right. Let's look at a couple of applications of all this. This is actually, I've done the MM's CK model, but I think the MM1 model will be enough to sort of illustrate what's going on. One thing that's quite interesting about the MM1 model is that if you're actually calculating individual waiting times, and WI is the waiting time of customer I, SI is service time, and TI and interval time, the calculation is actually just this really, and it's very simple updating. Now, at first sight, it doesn't look like as if you can do this in lockstep because it involves an if-then statement really. So there's a branch, but if you know C at all, you know that there's actually a ternary operator that will actually carry out that calculation. So in fact, you can actually carry out this calculation in lockstep, and that's what I did. And this is the first example of a kernel application. It's just basically a subroutine. If you actually look at it, you just say, well, you know, what makes it a CUDA program? Well, it's basically entirely C. The only thing that sort of makes it distinctive is what I've highlighted in this magenta, the thread index. These are system variables which the kernel knows about, and it identifies the particular thread. So the TID, the thread index, is an individual index which identifies a particular thread in a particular call. And that's the only thing that really makes the thing so parallel. So when you launch kernel, you just launch this, and the compiler would then ensure that each core gets its own version of this piece of code with a different TID, and that's all that happens. As is actually a simulation, it needs a random number generator, and I'll say something about this. But there's an initialization of the random number generator for that particular thread, which involves TID, which makes it individual. And then there's the little loop, which actually does the updating that we just saw in the previous slide with non-customers. In my simulation, it was 50,000 customers. So the call would simulate the waiting times of 50,000 customers, and the crucial if statement is handled by this single ternary operator in C, which does the updating depending on the text in it to assign the value of W to S or B. And the answer is then put in the estimate. That's the average of the waiting time of the 50,000 customers, and depends on how many threads you've got, how many of these runs you're actually making. Just a word about the CUDA uniform generator. It's quite a sophisticated thing in the sense that it will handle the parallelization for you properly. The whole generator has got a period. It's actually an exclusive OR bit shift generator with a while generator attached, so that gives it a very long period. And the initialization allows you the usual seed, but it also allows you a sequence parameter, which effectively we're going to set equal to the thread. So that basically means that a different sub sequence from the full period is picked out and used for each individual core. So the threads are running independent versions of the simulation. Each thread will sample up to 10 to the 20 values, so it's a pretty large number of random numbers available in each segment, and you've got, I don't remember how many, it must be sort of 10 to the 30 odd different sequences available. Very easy to do. So well, here's the punch line. Running this with the grid size and block size is set there. There were 7,000 odd runs, and on this it took 0.8 of a second. So in the time you say Bhakti, it's done. I mean, it's not a very complicated simulation, but you know, you were doing it on the CPU, and it takes sort of half a minute when you're sitting there. So in terms of what Sally was saying about, you were talking to a busy chief executive, it does allow you, I think, really fast demonstrations, and certainly I think that's how I was thinking possibly sort of using it really for really sort of immediate sort of face-to-face demonstrations. This is the sort of speed that you're getting, which is, well, in fact, in one of the other examples, so that was a 30-fold increase. I've also executed a more realistic MM1 model where it is actually an event-based, proper discrete event simulation, but as it's simple, you only need to check whether it's an arrival or a departure taking place. But there's proper sort of if then else types of coding in that really. And the good news is that in terms of the actual speed, it was actually when things slightly faster. It was like over 30 times faster. Again, it's a little bit more complicated, so it was taking over a second, but the CPU was taking nearly 40 seconds. So that's the sort of speed up you can get with examples like that. Same thing with the MMC KQ. I won't bother to go into that. Let me just finish off with a statistical example, which I think is quite interesting. In a lot of statistical inference problems, you need to calculate the likelihood function, which involves a summation of log densities. And if you're using the method maximum likelihood to estimate the parameters, what you would want to do is to identify the theta, which maximizes the log likelihood. And you might use, say, a method like, say, Nelda-Mead. Now, the example I've got is actually a realistic one in that it's actually estimating fitting a finite mixture model with k normally distributed components. So the density is actually itself quite complicated. I've just written the k plus 3 version with 3 components, but the example I'll show you actually allows you to vary the k and fit 2, 3, 4, 5, up to 10 components. So you can have a really quite complicated sort of data sets. Each of these are individual normal densities. So in this example here, you've got really a very large number of variables involved, and if m, which would be the number of thetas you have to look at when carrying out a never-delete search, and n, the actual sample size, is large, this can be a very expensive calculation, just working out the likelihood on its own. Now, rather fortunately, and this applies really, you see, to much more widely than just the example I'm talking about, the log likelihood only requires the calculation of individual terms, each of which is a log density. So the calculation of each of these is all identical. So clearly you can parallelize that very easily. And the other thing you have to do is to then just simply add them all up in order to actually form the log likelihood. And summation is also something which is amenable to parallelization. I've got, I think, the code here for the calculation of the individual terms. And again, you see, it works in exactly the same way. The little loop here in the kernel is just simply working out the separate components and putting those together. And again, here's the thread index, the J. That's the thing that identifies it as being code to be treated as being parallel with, for each thread, a different calculation being made because it involves different YJs. Right? So that's the bit that makes it parallel. So the result here forms all the log likelihoods, the log densities that you have to add together. And then the other thing that you need to do is to actually add them together. And this is a well-known operation called reduction in parallel programming, most easily explained by looking at the case when you've got to the power d terms to add together. Rather than going through this in detail, I'll just show you through an example. If you're adding, say, 2 to the 3, 8 numbers, you just add them in pairs first, then add the pairs of pairs, and so on. And the number of steps required is the power, the log n. So it's a log n operation. So it's really very, very, very quick. If you're actually just calculating the log likelihood, then it's a speed up of something like 120 times, just for the calculation. Now, obviously, in the full domain, there's rather more calculations involved. But here, and if I can show you the example, it's actually a credit risk example, which was quite an interesting example with sample size of 7,000. I took subsamples of this and also 2 large samples where I sort of doubled and quadrupled the number of observations. Did a K-component normal mixture model fit. Here's the actual fit for the 5-component model. So it's really quite a complicated data set that we're looking at, and it actually has a very big spike here, which has turned out a quite interesting interpretation in this credit risk problem. But the sort of crunch results are shown here, and you can see it depends on the sample size. You see that for small samples, well, CPU and GPUs are sort of pretty quick anyway. But if you've got large samples, the GPU was basically taking a minute to do, and this was far sort of lot longer. The speed up was nearly sort of 70 times. Really. So for something which was really quite a significant calculation, this was really quite a good one. So I think that's basically it, really. I think there's a lot of sort of potential with this kind of card. What I haven't sort of looked at, which I think is probably critical, really, is the memory management side. And that's probably where the big sort of bottleneck is.
So I feel like I'm rushing you there.
Yeah, right.
I'm concerned that there may well be some questions.
Yes, sure. Yes.
Can I open it up to questions?
Are you aware of anybody else doing this? I mean, how did you get interested?
Well, I suppose I did actually put a lot of consultancy work on graphic rendering at one stage, really. So I've always been quite interested in the parallelization involved in the graphics cards. And then I noticed that NVIDIA, originally they just modified their graphics card, so you can actually use a laptop version, but it's the processing isn't quite so sort of general purpose as one would like, with the floating point side of things wasn't really handled all that sort of neatly, really. And when this card first came out, it was still too expensive, but after a couple of years, and the prices started to drop. In fact, I noticed just 2 weeks ago, one was actually sold for just £250, which is rather irritating, that because I would have snapped out, because you can parallelize the cards as well. And it seems to me that it's clearly an area which there's certain sort of research fields like particle physics and financial modelling are using really quite seriously. And in fact, I was speaking to Israel Vieira, a former research student who's working for Formula 1 racing Red Bull now, and he uses these all the time. And of course, they've got a full-blown setup for flying. So he's probably the person who one should talk to, really. He helps with really do it.
Any other questions have we got? Yes, sir.
So I just want to make sure I understood on the last application. So the Nelder meat is not parallelized, right?
No. It's just in question. But it's just simply because the computer-intensive part of the Nelder meat is just simply the evaluation of the objective function, the likelihood, and you just simply parallelize that. So I think for that reason, if you actually use a better card, there's always the bit, the sequential part where you're deciding which theta next to select, which will not be parallelized.
Mark?
Russell, you might have really answered this just now, but are you saying that kind of graphics card that you put in your average laptop, although it parallelizes to some extent and
Yes.
it's got much fewer cores than this,
Yes.
it also can't do this because of some other feature this has?
I've not really investigated it. I never sort of, when I looked at the details of the sort of cards, it was clear that they were still targeting a graphics audience really, and they were sort of saying, well, you can do all this general computing really, but when you actually looked at the examples, it's all related to the graphics and the rendering side.
Can I answer?
Yeah.